Okay, so it's working. I just check the okay. So it's recording and streaming also on YouTube. So sorry, apologies for the delay. We will start lecture now. Before we start, I want to ask you some questions, and I can see all of you have laptops up, which is very good. So how many of you know Bitcoin? What is Bitcoin? So what is it? What is Bitcoin?
Cryptocurrency.
It's a cryptocurrency. What does it mean? Yeah. So first, what is cryptocurrency? What does that mean? Yeah, digital currency. So we have some keywords: digital currency. So what does it mean? What does it mean that it's a currency? What's a currency? Exactly. So we can pay. Okay, so what else it means? We can do transactions. Right? So what does digital mean? We can do digital transactions digitally. So if Bitcoin is a digital transaction system, we have to have some way of transacting. So we have Alice and Bob, and they can send the Bitcoins to each other, right? Okay, so to send Bitcoins to each other, what do you need? What Alice and Bob need to have? What do they have? Yeah?
Computer.
Computer? Yep. What else? Yes?
Internet connection.
Network? Yeah. What else?
Address where they should exchange the money.
Say it aloud.
The kind of bank account or public key for Alice and Bob.
Okay.
And then Alice know where it should put the money.
They need to know the address, right? What else? Yeah.
A specific program to do the transaction.
Yeah. So a program to manage the addresses, and there was a public-private key that the program also needs to manage for them, right? Anything else they need? That's about it. So what is the format of the Bitcoin address? How does it look like? Yeah, so it's a string. Is it okay, Google it. So let's check. Bitcoin address format. Okay. So, okay. It turns out we have three types of addresses. One which starts with 1, the other one which starts with 3, and then we have the new one which starts with characters BC1 or something like this, right? So if you were to run a quick check on your computer to find out how many Bitcoin addresses do you have on your drive, what would you do? So the question is, how many Bitcoin addresses can I find on your hard drive right now? How would I do that? How would I check it? What's the simple way you can do it? Yeah?
Go through all files and see if they begin with one of these three, like if they begin with 1, with 3, or BC1, then the length maybe also.
Yeah, so in general, if you were to search text files for some string inside, what do we usually use? If you need to find something, if you need to find a telephone number or email address or something like this, how do we search? So we go here and we say find, and I have a search field and I type something, right? So I don't know, BC1, but that's exact search, right? I'm searching for exact thing. But if I want to be a little bit vague, what can I use? Regex, regular expressions, right? Do you know regular expressions? Right. Who doesn't know regular expression? We'll Google what it is. What we want is Bitcoin address regular expression. And Stack Overflow comes to a rescue. Do you know Stack Overflow? Yep. Those who are programmers know. Stack Overflow is a kind of a question answer site for programmers. So we go here and we have a bunch of answers, right? Is this a good one? Not really, because in fact we don't use the full spectrum of characters, right? So base. There is a Base64 encoding, which uses the full ASCII spectrum for encoding in the ASCII way some binary data. Do you know Base64? We use it for email attachments, for example. So emails SMTP protocol doesn't send binary things. It has to send everything as ASCII. So if you're attaching binary file, it has to be converted and coded as something, with the ASCII character set. Then it can be sent over the wire, and then on the other end you kind of unpack it to a binary file again, right? So sending, large attachments over email is frowned upon, mainly because if you have 1 kilobyte of a normal binary data and you encode it with Base64, it blows up because you have to use the ASCII characters only, right? But there is another one called 54. Do you know Base54? Who knows Base54? So it's actually Base56, I believe. Yep. Let's check. Base. Yeah. So base 60 P58 and base 58. Which one is which? It's base 58. So if we restrict the characters that we're using, so for example 0 and O are confusing. If you have some sort of a keyword which is encoded with base64, and it will use zeros and capital O letters and I, capital I and lower L, they are very hard for humans to distinguish. So if you were to visually see a difference between two keywords, or if it's a password or something, then usually you don't know whether the I or L is I or L if it's in the password. So this encoding gets rid of all the confusing characters, and it's restricted to a subset, which makes it visually unique, right? You have no confusing characters. So this regex uses all possible characters, but the Bitcoin addresses are encoded using base 58 in such a way that it's easy for humans to see the difference. So there is an attempt to make it better, and so on. And if we scroll to an answer which has 0 upvotes, it turns out to be the best and the most accurate pattern, right? So here we have a regular expression pattern that encodes correctly all the Bitcoin addresses. So now if we have that, I copy that, what would you do to search your file, to search your hard drive? How can you search your hard drive using regular expression? If you're a Windows user, how would you do that? And if you're a Unix, Mac, or Linux user, how would you do that? How would you find out? Do you know how to do it? Yeah?
So we can use grep with the regular expression.
Perfect. So we can use grep, right? So I will drag my console. Okay, so that's my terminal. So I can use grep with the regular expression, and to search my entire hard drive, what would I need to use? Grep from the root. Right, so let's see. How do I do that? I have to say -e and the regular expression pattern, and then I specify which files do I want to search. It will search if I say grep e and if I do root, yep, it's a directory, fair enough. I need to run, I can search directory, but I have to say I want this search to be recursive. So what grep is currently doing is going over all my files, including the ones I don't have access to, and all the binary files in a search of that pattern. Is that correct? So run it on your laptops. So run grep on your laptop to check if it will find anything, if it will find any Bitcoin addresses anywhere in your file system. Okay? I will let it go. How would you do it on Windows? Is there a pattern matching utility like grep on Windows? Okay. There is a command line tool called findString that comes with all Windows NT class operating systems, and you can check how to use it with saying /?, and it will tell you how to put a regular expression in it, and you can run it same as grep. So what we're currently doing is a kind of a very typical activity of a digital investigator who got a suspect hard drive, and it's running a very quick scan to check if that suspect had any dealings in, in Bitcoin cryptocurrency. Normally, you would combine multiple patterns into the regex. You wouldn't only search for the Bitcoin, you would search for other cryptocurrencies at the same time. And also, while you're doing it, you would log all the discovered crypto addresses into a database, so you can do a check against the blockchain later on to see if those addresses actually have been used. Because you may find out some addresses which were never used, or some addresses which don't have any incoming funds, or you may find out just keys which are encoded using the same schema, but they don't actually are valid blockchain addresses. So to validate, you would have to consult the registry of the blockchain itself to see whether those addresses are of interest or not. So are you running the? How many of you are using Windows? Yeah. It's harder to do stuff on Windows, to be honest. When you're doing any of those type of investigations or searches, usually the toolkits, the tools that you have available on Windows are much more restricted. It's much easier to do them on Unix-like system like Linux or Mac or any other Unix-like operating system, because you have more command line tools that you can use. Where else would you do this scan? Let's say you find out a dark marketplace forum leak, okay? Some, million of messages from a dark web forum or something. You would like to scan the forum, which is usually a bunch of text files for the addresses as well. Okay, so while the computer is doing their job, so far I have not found anything. Why do I get those permission denied messages?
Also don't have access to read it?
I don't have access to read those files because I'm running it as me, as a user, and those files are owned by another user without giving the read permissions. So I would need to make myself a super user to be able to browse everything, right? All right, so while it's doing the task, let's talk a little bit about me and then about you. So I'm a lecturer here. I'm a computer scientist. I work with the computer science department, but I do some projects on cryptocurrencies with the cybersecurity department. So I sort of I'm involved with both. I work mostly on peer-to-peer systems and multi-agent systems and autonomous systems. And I also help with the game program. So I teach game design and game programming. I teach cloud and mobile computing too. So anything to do with programming and with modern computing systems. Yeah, I love hackathons. 2 years back, I went to Dublin for the blockchain hackathon, and funny story, I got the award for together with a team of 5 other people for designing art sharing program on top of Bitcoin blockchain that allows artists to kind of sell and combine different digital assets. We won the award, and they asked me, okay, do you want the 400 euros in cash or do you want it in Bitcoin? And I said, yeah, it's fine. I take it in Bitcoin. So it was about one Bitcoin at the time. So now it's worth, almost 10,000 euros, and I would get 400 back then. So sitting on some Bitcoin over a period of time tend to be valuable, but it doesn't mean it will continue like that, right? So over the last few years, it's been upward trend with some wild fluctuations, but the uptake was sort of making Bitcoin more and more valuable. And then I also like running. I'm a long distance runner. I like climbing and flying. So the longest run I've done was a 24 hours ultra marathon, where you start on Saturday morning, 9 o'clock, and you run for 24 hours to Sunday morning. And then they shut the gun to kind of for everybody to stop, and they measure exactly how far you've run. And I've run a little bit over 160 kilometers, which is a little bit disappointing because there is a very nice ultra marathon in Greece, which is 246 kilometers, 248 actually. And to qualify for that race, you have to run 180 kilometers in 24 hours. So I was, 20 kilometers short to qualify. But, it was the most mentally exhausting activity I've ever done. You run in a 2.5 kilometer loop. That particular event was like that. So it's very monotonous. And you get really exhausted. So about you. I would like to ask you some questions. So, do you know what hashing is? Who knows hashing? Yeah, one-way functions, right? Do you know some examples? Can you give me some hashing algorithms? Yeah, SHA-1. Yeah, great. Do you know this one? Who doesn't know that one? Okay. So NSA designed the SHA family of algorithms, whereas this one was designed by the open academic community. So the history is slightly different. And this one typically is 160 bits. Why do I mention it? Because it's the one being used in Bitcoin and some other crypto. Okay, what is a collision? Yeah? Correct. So if I have two distinct inputs and I use the hashing algorithm and they give me the same hash, I have a collision. And why it is undesirable? Why do we don't want that? Yeah? So sometimes there is no wiping thing. So sometimes I have a large collection of data items. So I have a large collection of data items, and I need to quickly search my collection, my list, right? There are different search algorithms. I can sort it, but usually if I want to have a very quick lookup, I would like to have, so I want to find out if particular input is in my list, right? So I can hash all the inputs that all the data that I have in such a way that I have a hash table. So let's say I have A, B, C, D, E, F, and so on. So I can hash my data structure in such a way that I have a hash let's say F, G, H, I, J. Okay. So now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 items. I split it into 3 buckets, and then let's say I have some hash 1, 2, and 3. Can I fit my 10 items into my hash table? I can't, right? Because I have to index 10 things and I only have 3 indices, right? So I will have collisions. So let's say I manage to get A and B, C and D, E and F, and G, H, and I and J into the buckets, right? So then if I have some input, I have an input, I don't know, let's say A, and then I calculate the hash and it gives me 1 for this input, then I have to search linearly through that list if A is in that bucket. If I get W and then it hashes to say 3, I have to do 1, 2, 3, 4 lookups to see, okay, W actually is not in my data structure, whereas A is, right? And I have a collision. I can hash anything to a value 1, 2, or 3, but for any input I will have a collision because my input space is much, much larger than my hash space, right? My hash space is only 3, whereas my possible input space is infinite, right? I can infinite space of potential strings, right? So collisions here are unavoidable and they will happen and we have to live with them, and normally we do that by having kind of a linear list for the things that collided, right? We don't want to do that because hashing and lookup is kind of a, requires one lookup, right? So for 10 items, it would be really nice if I can do a hash of 10 values, and then I can index everything by the hash. So then for A, I go, let's say A hash to 1, and then there's only one value. So if it hashed and it's there, I have one lookup for the hash and one lookup for the list, and I'm done. For W, if it hashed to 3, but on 3 I have D, then I compare, okay, W is not there. So I have one lookup here and only one comparison, right? So if my data grows, I would like to have the hashing done in balanced way, so I have little lookups. But with algorithms like RIPE-MD or SHA-1, why do we don't want collisions? Here we can live with collisions. But with those other algorithms, why collision is undesirable? Yeah?
If you, for example, want to digitally sign a message, then somebody else can find another message with that first. So usually we hash the message first and then sign the hash.
Yeah.
It's shorter.
Yeah.
That's a given length. And if you can find another message with the same hash, you can change the message.
Exactly. So I have some sort of message, and I calculate the hash, and then of that message, and then I kind of give Bob some sort of proof, so he can verify that the text in the message is what he received by comparing the hash or comparing the signature of the hash, right? So then, if the hash is not unique, what it means that there is a different message with different data here that hashes into the same validation, and then Bob checks it and says, yes, it looks valid, but the content of the message actually has been subverted, right? So we don't want hashing to have collisions because that allows adversary to kind of fake messages. So is it possible for, let's say, 160 bits to hash uniquely any possible messages? Clearly no, right? The space, the input space is pretty much infinite, and here we have a finite space of the hashes, right? So we will have collisions, right? Okay. So if we know we will have collisions, why we still use that? Why we still trust it? Yeah?
Because it's hard to find the endpoint.
Exactly, because it's extremely hard to find the collision, right? So we want the process of finding the collisions to be really, really hard, which gives us to the third question: what is the avalanche property? Yep. Correct. So avalanche property is a property that if I have a function which takes an input and produces an output, and my hashing function, and I have a string of bits in the input, and I change just one bit, it results in almost all the bits being changed in the output, right? We want the small variations, small changes here to result in a huge random changes on the output of the hashing function. Okay, so this hashing algorithm is a fundamental piece of technology being used in Bitcoin. It does rely on the fact that it's really hard to find collisions, and also all the good hashing algorithms have a good avalanche property. There are other technologies which are used. So how many of you know Bittorrent? Yeah, you use it? How Bittorrent works? Do you know Gnutella? It was sort of a peer-to-peer file sharing technology before Bittorrent, a few years back. Yeah?
So for Bittorrent list, so you have different peers that share data between each other.
Yeah.
So you have some data, I have some data, and then you share between them.
Yeah. So let's draw it. So I have, again, let's say I have Alice and Bob and Charlie. So they have some files. Let's say Alice has F1, Bob has file 2, and Charlie has F1 as well, right? So now in Gnutella, there is a registry which these guys advertise what files they have. And Charlie says, okay, I have F1. And Alice says, I also have F1. And this guy says, okay, I have F2. So this guy says, okay, I need to download F1, right? So what happens is he starts downloading F1 from Alice. So he has a copy of F1 now, but he kind of downloaded up to that pointer, right? And then Alice went offline. So then he consults the registry and says, that's not a problem because Charlie has F1 also, and I will just start downloading from him from that bit and get the rest of the file, right? So that's how Gnutella worked for file sharing. People were advertising files of what they have, and it allowed the downloader to download a file from 1 or 2 or 3 providers, given which one was kind of online at the time. But what's the problem with this one? It has 2 problems, let's say, more than 2, but 2 main ones. So the one problem is that I can only download from one source at a time, right? While he's downloading from Alice file F1, you can only have one sort of download happening at the same time, right? So that kind of tells you, well, you know, obviously, what we can do is we can say we can split the file in 2, and he can be downloaded from that point from Alice, and from that point from Charlie. So he can be doing 2 downloads, one happening from the beginning and one happening from the middle. And this is from Alice and this is from Charlie, and he can be doing 2 at the same time, right? Is that an improvement? Of course it's an improvement, right? So the other problem is that you cannot advertise that you have only half of the file in Gnutella. You have to have the entire file. You cannot say I have from half to the end, right? And that's basically what Bittorrent did. It said, well, you know, the original system is great, but it's a little bit inefficient. How about we just cut the files into chunks, okay? We can cut files into chunks. We can hash the chunks. And instead of advertising that you have F1, you can advertise I have F1 and say which chunks you actually have. If you happen to have the entire file, that's great. You just advertise you have all the chunks. And if you'd only have, say, the beginning and the end, you just say, okay, I only have the beginning 3 chunks and the end 3 chunks, right? And then when Bob wants to download a file, he looks the registry and he says, okay, these 2 guys have, you know, those chunks, and I will be downloading concurrently as many chunks as I can from the seeding peers that are offering me the file. Is that simple? It's super simple. Like, you know, if you think about it these days, you would come up with that yourself, but it took, you know, it took us years to come up with such a simple scheme like Bittorrent to have it actually working. So instead of storing the entire file, you can store just chunks. And instead of downloading only from the beginning and resuming when the peers go off, you can download from any chunk that you have the file. Okay. So consistent caching. How many of you know what that is? Okay, we will not go a lot into details, but just a simple thought experiment, okay? We need to find where people are and how we kind of can download stuff from them, okay? So if you go online, you have an IP address and you have to kind of advertise yourself in the registry, right? So imagine that we have a ring that hashes everybody's IP address to some sort of value, right? So we have hash 1, which is for certain class of IP addresses. We have hash 2, hash 3, and hash 4, right? Let's say we only have 4 hashes. And now when you go online, you will be kind of attached to one of the buckets, right? So you go online and you hash to a particular value. So let's say you hash between H1 and H3, somewhere, your hash is bigger than H1, but so H1, your hash is bigger than H1, so you are here, but you are smaller than H3. So you are somewhere here, right? Let's say you're here. And new people come along, and they also hash somewhere. So they hash here, hash here, hash here, hash here, and so on and so forth, right? So you have some sort of a hash function which takes your IP address and hashes it into a value, and you have values which are so that if you have a progression, there will be kind of a gap somewhere, right? So you will have a kind of a minimal value, and then let's say here, and you will have the maximum value, right? And then you have the kind of a ring. So now if we have, say, 5 nodes, it's pretty efficient. But as we saw here, if I try to do 500 nodes, then the lookup of the buckets, because now if you are between H1 and H3, you kind of add it to H3. So you are here together with some other people. And then people who are between the minimum and H1 are kind of here. So if we have a large number of people, we need to add kind of nodes. So we would like to add a new hash node here, 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 and here. And then now if you were here, you still are at H3, but all those people who are here become kind of attached to that one, right? So if I do that, if I introduce additional nodes, I have to rehash the space. And I would like to do it in such a way that my original hashes still point to the values that it had, right? So by adding new hash entries, I don't change the hashing of the existing ones, but these guys here will have to be changed over, right? So on average, I will have, so these guys have to be rehashed, because now instead of hashing to H3, they hash to, say, H6, to this one. These guys will have to be rehashed, and these guys will have to be rehashed, and these guys would have to be rehashed to this one, right? So on average, I have only part of the population to be rehashed to the new keys, but the rest stays the same. And it's the same if the node goes down. So if I say have H9 here, and this node goes down, then these guys which were hashing to H9 now have to hash to H4. So now, like, these guys already hash to H4, but these guys have to now change to hash to H4, right? So consistent hashing is a kind of a hashing property of the system which allows adding or removing kind of a hash nodes in such a way as not to disrupt everybody, but only disrupt, you know, subpopulation of your hashing scheme. And it is kind of used in some of the algorithms for distributed hash tables. We use them to kind of be able to look up the peers in the distributed peer-to-peer network. All right, 2 more technologies to go. So what's IRC? Yeah?
So internet relay chat.
Yes. Do you use it?
Yes.
Internet relay chat. It's a network of servers which are all connected to each other, and they relay text messages between users. And you can have peer-to-peer messaging for direct messaging between the peers, or you can have one-to-many messaging through the servers. So it was one of the very first you know, application layer protocols which was facilitating kind of a text communication for humans. So all the, you know, Twitter, Facebook's, you know, social network types of applications kind of get the inspiration from the IRC. And IRC is still operating, and it's a large number of IRC networks that you can plug yourself into, and then you have, you know, a number of users kind of using it. Programmers use it, some companies use it for support, and a lot of open source projects use it for Q&A and for kind of, yeah, for, you know, kind of an office replacement where you can chat with other people working at the same time. It's not as popular as it, you know, as Facebook. It doesn't have billion users, mostly because the user interface is a little bit of geeky. You have to use a particular client software, and it's not as seamless as, say, with Facebook, but it has its uses. And in particular, why do I have it in here? Any guesses? What do you think why I have IRC in the list of technologies which are useful for cryptocurrencies? Yeah, any ideas?
Yes.
Yeah?
So IRC serves as this principle that you have a split of multiple servers connected together. Once one server goes down, you have a split, and then the other servers are still connected in the same network.
Yeah. Good. So, so one guess is, let's say, split mechanic. Right? So, normally you have a network of servers connected to each other. Okay? Well, they usually don't duplicate too much. Okay, so let's say we have something like this. So I have a bunch of servers connected to each other, and you have humans chatting, right? So if these guys are sort of chatting, this guy is connected to this server, this one to this one, and I have Alice connected here. And they kind of chat. They see each other and they chat, right? And now a split happens, so one of the links goes down, and the network gets partitioned. So now these guys see each other and they still can chat, but Alice doesn't see them and they don't see Alice anymore. They sort of are in a different universe, right? So if they chat something on the same channel with the same name, the channels kind of split, and these guys see a different history of what is happening, and Alice sees a different history. So split mechanics is one kind of a similarity to split in the blockchains, right? But what else can the IRC be useful or used for in the context of cryptocurrencies? There are two main points. So what do you do if you want to buy some Bitcoin? You need to find a seller. How can you do that? So for buy and sell, what options do you have for buying and selling? If you had to buy, you can go to some exchange, right? We can go, for example, to Bitcoin.de. It's a German exchange. You register with them and you have the current ask price for buying and for selling, and they basically match buyers and sellers together. So if you want to buy, you just need to find a seller which will sell you for the price you're asking. So these guys are asking for, you know, 69999, and there are some people who say no, we want to sell for 7 or something. And there is a kind of a matching engine which matches buyers and sellers, and then you can sell, right? So you can go to an exchange. What else can you do? So exchange is the more the dominant way of acquiring cryptocurrencies. But the disadvantage is you have to register, you have to get validated, verified, and so on and so forth. And in the early days, there were no exchanges. Okay, so what else can you do? There is a system called local bitcoins. Again, local bitcoins is sort of like an exchange, but instead of having a kind of a centralized place, it matches the buyers and sellers based on their location, and it's sort of like a mobile app which allows you to find who else in Jovic has Bitcoin for sell or for buy, and you can kind of meet with them and you know, transact. So local Bitcoin. And the third one is you can sort of do over the counter. You can say, okay, who wants to sell some Bitcoin or buy some Bitcoin here? And you can do it between yourself, right? So that's usually called over the counter. And that's what original idea was, that there is a channel which you can go and people advertise, okay, I'm here and I want to buy, or I'm here and I want to sell. And people can match using IRC channel the offers for sell and buy and kind of transact, right? So on Freenode it's called Bitcoin OTC, right? So yeah, you can see the Yeah, those. This is like a website which gets data from the channel to kind of extract some of the orders. But what's the more important one? So that was important in the early days, but these days you have other options. This became, let's say, niche. Those are more mainstream. But what else do we need for the system to work? So let's say you do have an address. You have a laptop, you have internet connection, you have a Bitcoin address, you have everything you need to transact now with, say, Bob. But how do you actually do that? How do you send the transaction into the network? How do you know to connect to what? You need to know some peers. You need to know some IP addresses of other nodes that you can connect to, right? So peer discovery has to happen somehow. How can you solve this? How can you advertise the peers in the network? So those of you who use Bittorrent, how do you find out other peers which have particular content that you need to download? How do you do that? Yeah?
Use trackers.
Use trackers. How do you find trackers?
Sure.
So in Bittorrent, you're here. There is a magnet or tracker list, right? So I have a kind of different protocols for getting a list of all those chunks, and I need to download it, but I need to find that, and then I will have all the IP addresses of all the seeds, peers, and all the nodes. But this file I need to download from somewhere. This piece of information, how do I download it? How do I know where to download it from? So, we need something here. We need something, so this file tells me where the chunks are, right? So all the chunks are somewhere in the network. This file tells me where they are, but I need to download that file. And how can I do that? So what fits in here? Any ideas? Search engines? Forums? IRC? Social networks? They are all kind of different sources of getting to that file, right? But that file I have to get from somewhere. So IRC is one of the mechanisms where you can share the trackers. You can share the links to trackers. BitTorrent search engines are kind of frowned upon by the intellectual property rights. They don't like them because they are sort of the entry point for getting into the BitTorrent networks. So a lot of search engines have been shut down by US lawsuits. But forums, messaging, IRC still allow people to share the trackers. So peer discovery is kind of a fundamental piece of puzzle for an end user to be able to connect to the network, right? So IRC is sort of used mostly for the peer discovery, not only in Bitcoin, but in other networks as well. It's a global network. It's quite robust. You can use it for messaging between the clients. So it's not necessarily humans actually using it. It's the client to client and node to node communication. But you can exchange some lists of the initial peers, and then the rest you can get from the peer discovery from within the protocol itself, right? So if I'm a node, blockchain node, let's say in Bitcoin, and I'm connected to some other blockchain node, I can ask the node for the neighbors for other nodes in the network. But if I'm starting up, bootstrapping, I have nobody, I have to get the initial list from somewhere. So I will get the initial list from the IRC channel. Okay, so let's have a 10 minutes break, and after that we will talk a little bit more about the cryptocurrencies. Okay, let's see. What happened here? Yep. So my search is still going. Nothing found so far. We talked about all the technologies. Oh yeah, 2 left. So FIFO and LIFO, easy. What's that? First in, first out, and yeah. So first in, first out, typical queue, right? So okay, first in, first out. I have a data structure, and things kind of come in from one end and go out from the other. So the first packet or block or whatever comes in, it will be the first one consumed. If there is a second one, so that was the first. If I have a second one, the second one is gonna get consumed, right? So FIFO is easy. Okay, last in, first out. What's the different name for that? Say that aloud. Stack, exactly. So a stack. That's right. So here we have something like this. We have some sort of base. You know, number 1 comes in, number 2 comes in, and number 3 comes in, and then I will sort of incoming and outgoing are kind of put on top of the stack, right? So why do I need a stack? So in blockchain, the FIFO is easy. I mean, I have a genesis block, and then it's linked to the next. So I have a block number 0, block number 1, block number 2, and so on, right? And if I have some transactions in block number n, I have some transactions here, and I have to verify that they are correct. I have to traverse everything from the chain link, chain list, right? I have a list of blocks. But how about the stack? Any guesses or any suggestions? Why do we need stack for? So in programming, when we, how many of you know Java? So Java runs on top of Java Virtual Machine, JVM. What is the JVM? Is it a stack-based virtual machine or register-based virtual machine? Okay, that's a kind of a, how many of you use Android? Yeah. So Android uses Java to program, but Dalvik, the virtual machine which Android runs, is a register-based machine model, right? Unlike standard Java bytecode, which executes stack instructions based on the stack-based JVM. What's the difference between the register-based and stack-based? that goes a little bit into computer architecture. So typically, I need some sort of language, some sort of assembly language, which is mapped to the machine language of the CPU. And that language needs operations like, you know, arithmetic and logic and sort of conditional operations. So let's say we kind of consider just addition, right? So how the normal assembly on, say, x86 works. It has an add operation, and you have registers like, you know, AX, BX, CX, and the add operation specifies which registers to use as the operands and where the results will go, right? So hypothetically, if I have an Intel CPU, I may have an instruction which says add from AX to BX and put the output into AX, right? So I will take the value out of the two registers and put the output into that register, right? And then the following instruction can move the AX value somewhere or do something with it, right? So those are my operands, and this is the result. And I'm using registers to do addressing. So the operation is here, but the operands are taken from registers and the result goes into registers. So that's what Dalvik is doing with the Java implementation inside the Android. But the normal Java doesn't do that. The normal Java does something else. It has instead of the concept of registers, it has a concept of a stack. And now I just have a stack. And my instruction to add two numbers is this, add. So this operation will take, let's say I have stack like this. This operation will take the top two elements from the stack, add them, and put it back on the stack. So this operation will do this, right? And then the next operation will, if it needs some operands, it will take them from the stack and put the result, if it has any result, onto the stack. What's the difference between this picture and this picture? Which one do you think has more instructions and more complexity in the instruction set? Register-based virtual machine or stack-based? Register, because we have to say where the operands come from and where they go. Whereas this one is very trivial. You know, to multiply, I just say mul, right? Here I have to say, well, you know, from where the operands come, where the result goes. What if I want to do CX plus BX goes to AX and so on. So even for add, I can have a larger number of different operations because I can source my inputs from different registers. And typically we use the accumulator A as a result. But even then, I may have 3 or 4 or more different operations just for addition. Here I just have one, and it's very simple. And if I have my instruction set, so let's say here I have some instructions like add, and I have some operands which I have to encode. So I may have kind of larger instruction set, and here I have a smaller instruction set, which means I can encode it into a more compact representation as well, right? Because I just have fewer of those. So Java and normal JVM is a stack-based specification which explains how the stack operands and what the instruction set looks like because it's easier, right? What is the disadvantage of this one compared to this one? Why Android hasn't followed the normal JVM? Why Android followed the new one, which is register-based? So this one is easier to specify, and it has a smaller instruction set. So why? What are the disadvantages of this one and advantages of this one? Well, if you think about it, all the current architectures of the computing devices that we have are register-based, right? We have Intel platform, we have ARM, and so on, and they all register-based. We have a concept of registers in the CPU. So if I have a virtual machine which is stack-based, I have to somehow map it to an actual execution environment which is register-based. And this mapping is more complicated for this than for this, right? The mapping here is kind of just, one-to-one. It's much more efficient and much more streamlined. And that's why Android is using this, because it uses less energy, less complexity to execute the programs, because they map naturally to the ARM registers. Whereas here, they would have to do a lot of heavy lifting, a lot of optimizations, and a lot of things to convert the stack-based machine to a register-based, execution environment. So this is a little bit more complex in terms of actual executing. This is much easier to map to the physical, hardware. This is easier and more less complex in terms of specification and in terms of mental model of how it works. So a lot of cryptocurrencies, including Ethereum and Bitcoin, which we'll discuss a little bit more in detail, are using stack-based virtual machine for the operations, for the actual execution environment, right? So because it is more simple to specify what sort of operations the virtual machine has and how they logically operate. All right. So we can move on. So we have a little bit more on cryptography. Not much, just sort of a surface level. We have the public-private key cryptography, right? So you know how public-private key cryptography works. You can use it for encrypting, you can use it for signing, and you can prove ownership with the public-private key cryptography, right? So you can hash the message to kind of validate whether the message is original, and the recipient can verify the message, and then you can encrypt the message, so then you know it was not read by anybody else but the designated recipient, right? So by signing, you can verify that a message was not tampered with, but everybody can read it. With encryption, you only the recipient can read it. So you have this kind of a concept of pseudonymous identity, because the private key is sort of like the identity of a signer, right? So what are the, we will talk a little bit about the, limitations of this in a moment. Why do we use elliptic curves in general instead of the simpler cryptographic systems that we were using before? What are the elliptic curves give us for public-private key cryptography? Yeah? That's right. That's right. So they are more, you could say they are more dense. So in a smaller bit space, we have more randomness and more difficulty of finding collisions, of finding things, right? So they offer us stronger cryptography given the same sort of size considerations. Exactly. Okay, so to talk about blockchain, we also have to have a little bit general understanding of what databases are. What is the normal database and what's the distributed database? what's the ledger, and how money works. So I asked you the initial question, and the term currency was sort of brought up, but there was no answer of what really currency is, apart from, okay, it's something we can pay for things. So very quickly, what's the database?
Collection of data in a systematic.
Yep, some sort of collection of data, usually indexed or usually organized in some sort of systematic way. Perfect. What's distributed database?
We have a number of databases, and when we query, we encode information from different databases.
Yep. Okay, so what you said is this. We have a database in one location. We have another database, and we have another one. And we have some sort of data stored in those, indexed somehow. And then I can run a query which will give me a result based on the various data that is distributed. Okay? And it can be done horizontally or vertically, right? I may have, let's talk about SQL for a moment. So I can have a table which has some sort of a primary index, and I don't know, name and surname, and it has 3 columns, and it has a number of rows. And now I can split the database in such a way that I have index, name, and surname here up to a certain point. So I'm splitting it horizontally, and then the rest of the database is here, and then the final bit is here, right? So when I'm running a query, I have to search the first bit, second bit, and third bit, and it's sort of split across 3 ways this way. Or I can have additional columns, so I can have name and surname here, and some additional columns here, and additional columns here. And then if I'm only searching for name, my query goes here because the other guys don't have name column, right? So I kind of split it vertically, right? So we have horizontal or vertical data splitting, or a mixture, right? With non-SQL databases, you have the concept of sharding, same with SQL, where you sort of distributing data in a particular way across the distributed nodes, right? Okay, so that would be fine if, imagine I have a database which has some primary index, name, and surname, and I have exact the same data here and here. Would you call it a distributed database?
It can be if it is, because distributed databases can be for performance as well. So based on your geographical location, you can have the same databases replicated at different locations.
Yeah, exactly. So you've used a good term, replicated, right? So if I just have the same data somewhere in different location, let's say I have it in Norway, so my queries don't have to go to US, we kind of call it replicated, right? We distinguish those two, saying, okay, actually the replica has exact copy. It's just that we're using replica because of location, of geographical location, of closeness to a particular user, right? And with replicas, what do you need to have? You have to have some sort of synchronization mechanisms, right? So if I have replica in Norway and a replica in US, and then in Australia, I have to have some sort of mechanism. I'm not asking queries anymore in the middle. I'm asking queries to a particular location because it doesn't make sense. So if I'm in Norway, I will ask this replica, but here I have some sort of a synchronization mechanism which makes sure that I have the same view over the data, right? So let's say there is some sort of a customer which talks to the US database, and the record was injected, a new row was injected, and I'm making query to my replica. Okay, what's gonna happen? I may have some inconsistency in the databases, right? Or the record was deleted, right? So this record was deleted, and I'm interacting here, and I still see that record in, right? So I have some synchronization issues and some consistency issues, right? The same with distributed databases. But those issues are kind of for both, right? It doesn't matter whether we're talking about replicas or whether we're talking about distributed databases. All right, so what will happen when your Facebook friend posts a post, it goes to the US database, and your Facebook client interacts with the European one? What will happen? Yeah?
Two things will happen, or one of the two things will happen. Either the synchronization has taken place and you will see the same thing.
Yeah.
If it has not taken place, you will not see the changes because there might be some lapse, time lapse. Perfect,
exactly. So if the sync already kicked in, you will see the consistent view. If it hasn't taken place yet, you will not see his or her updates, right? Okay. In social networking, how significant is that? It's moderately or very little significant, right? If you see somebody's post with a bit of a delay, nothing bad will happen, right? So if we take the financial system into account, though, having a money into account or not having a money into account has a huge implication whether I can spend them or not, right? If this person already spent the money and then tries to double spend it from this database, then I have sort of a problem. I really cannot allow that. So I have to make sure that the synchronization and consistency is much more strict, that if that person initiated something in the US, then it is sort of an atomic transaction in such a way that the replicas will reflect the same consistent point of view, right? So how would you do that? How would you do that between Norway, Australia, and US, we see the consistent view, yeah?
In the banking system, I would keep the synchronization period shorter than the transaction period.
Mm-hmm.
So for example, if I have that transfer and I hit the button, there's always some processing time.
Yeah.
I would keep that longer than the synchronization time.
Of the databases, yeah. So you have to have some sort of control and some sort of a mechanism for enforcing some of those rules, right? You have to enforce that the transaction time is longer than the sync time. You have to enforce sort of a global consistency. And usually in the banking system, you do that by having some sort of a trusted third party. So you have some sort of a clearinghouse or a bank which kind of processes the incoming and outgoing transactions kind of centrally, right? So if you have a bank account and you are spending money from that bank account will lock the funds in such a way that you cannot really double spend it. And with the bigger financial institutions, you have, some intermediary clearinghouses where the funds are kind of being locked for a while. And that's why cross-continental money transfers take a long time, because each of those intermediary, they take this precaution of locking funds for a while, right? So that's how it works. If you remove the trusted third party, it gets a bit complicated, right? So we need to have some sort of mechanism, some sort of a consensus mechanism, which all the independent peers will agree that, yes, that's the consistent view over the database, right? And that's what we use the blockchain ledger for. Okay, so what's ledger? In simple terms. Yes. So a ledger is, I don't have a slide, but a ledger is a very simple list of all the transactions. So if Alice and Bob have some sort of a history, and at initial point, Alice had 100 and Bob had 0, and Charlie had 0, at Genesis block, then if Alice sent 20 coins to Bob, there will be a transaction number 1 which says Alice now has 80, Bob has 20, and Charlie has 0, right? So a ledger is basically a list of all the transactions that has occurred and the current state of accounts, right? So we know that Alice has 80 and Bob has 20. With the pseudonymous identities, we don't know their names, we only know the addresses, right, of where the funds were coming from and going to. Okay, what's barter? So in the old days, before the concept of the currency was invented, how people were trading with each other? Exactly, they were exchanging goods. So barter is basically a good exchange. So I have something like, I'm gonna go to your home and fix your computer because I'm a computer scientist. I can install your antivirus, and then you will come to my place and help me paint the room. Okay, it's barter, right? I exchange my service for your service. I am a farmer. I have some apples, and then you have cows. I will give you apples. You give me milk. Okay, what's the problem? What's the problem with that?
Value of the goods differ.
Yeah, so one problem is that the value is sort of so okay, so let's say barter. So you have to match two people transacting in time and in need, right? So it must occur that what I have right now is what you need, and what you have is what I need, right? So if I have Alice and Alice has I don't know, so Alice has apples, and there is Bob who has what Bob can have some buckets, okay? But Alice doesn't need buckets, but there is Charlie, which has a need for buckets, and Charlie has, some cards, and she needs cards, right? So she could give apples to Bob, Bob would give buckets to Charlie, and Charlie would give the cards to Alice, right? So barter economy can have more than one, like you can match needs, but they all have to kind of match at the same time. And the needs and the time, it's kind of complicated, right? And also, if I have apples now, but in a few months you will have buckets for me, I have to keep a ledger of what I gave you, so you owe me something, right? So I have to have some sort of accounting that, in autumn I gave you apples, so in spring you will give me potatoes, right? Because, they don't happen at the same time. So it gets a bit complicated. So, for example, to solve some of those problems, there were some interesting phenomena occurring. So, for example, in New Zealand, there is a concept of koha, which is like a gift economy, where, I give you apples because I have plenty of apples, so I give apples to my friends, right? And then in spring, when they have a lot of potatoes, they will give me gift of potatoes, right? And you kind of expect this to happen, right? So there is like a tradition of giving gifts and then receiving gifts when other people have more than they need, okay? But, it is still inefficient. It's much less efficient than transacting with money, right? So what we can do is we can have some sort of value in the middle, right? Which is sort of the exchange representation. And then I give you apples, and instead of you giving me the buckets, you give me this, you give me money. And then this guy needs buckets, so he can pay you money for the buckets. And because this guy is producing cards, I can pay him for the cards. And it's sort of much more easy to transact with those three properties, right? So Yeah, so we went through this. We had the pre-money era and barter-like, so gift economies and barter exchange methods. We had some commodity money, so we could use something as an means of exchange. So, for example, in ancient Egypt, they used barley or some grains, and then later, gold and silver. There is an interesting concept. 600 years before the Christ. There was an island on Pacific, which was using kind of a huge circular stones as a value of money, right? So you can check it out. They had to travel. So the stones were quite huge. They have to travel on tiny boats to an island which was a little bit far away, carry those large stones back to this island and shape them in a certain form, and that represented a value, right? And it was really difficult to fake it because there was no stones on that particular island, so you couldn't really fake the money. And you can say, okay, I'm gonna sell you a house for half of that money that I have, but then they had to keep a ledger of who owned which part of the circular stone in one, because they cannot really shuffle them around. So the stones were lying around the island, and everybody knew whose part is whose, and they were sort of keeping a ledger of who got married with whom for how much, and whose house is worth what, and so on. And that is kind of very interesting concept of money. Like we these days would think that's ridiculous, but it was basically working as a kind of a value exchange in the era where money were not invented yet, right? So they were using it, and this is sort of considered as a very precursor of money in the very early days. Same as gold and silver, but these were more they were more dividable and they were more transferable, right? So you could actually give somebody a bit of silver, right, and they could carry with them, whereas this was basically a form of ledger. Right, so we have the three properties. So money is some sort of medium of exchange. It's this kind of an intermediary medium, so I don't have to exchange my apples for your buckets. I can exchange my apples for this something, for this virtual thing. It is a unit of account, as with the Rai stones. It sort of keeps our ledger kind of in sync. So we know what value it is, and we know how much people own each other, right? So it's a unit of account, and then, as we were discussing, I have apples in autumn, but by spring the apples will be rotten, right? I cannot keep them. I cannot keep them in my storage. I mean, people did. They stored grain and they stored some animals and so on as a store of value. But some things will kind of, lose value quicker than others, right? So gold, for example, doesn't lose value. I mean, it's the same gold today as it will be a year later. If I have 1 kg of gold, it will be 1 kg of gold, right? But if I have a ton of apples and I wait, half a year, I will have nothing, right? The apples will rot and I will lose my value, right? So I need something which, I can exchange my apples for, so then in spring I can recuperate, regain the value of the investment, right? So those are the three functions which money or currency basically exhibits, right? So we discussed the double coincidence of wants. Unit of account. Okay, so for example, so we have relative worth, standard of deferred payment, concept of debt, divisible, countable, fungible. What is fungible? Do you know that word? Yeah?
Equality of exchange.
Yes, exactly. So if I have a one US dollar and I have another $1 US, can you distinguish which one is which? If they are banknotes, you will have a serial number, right? So you can kind of distinguish it. But if I basically have it in the bank account, I say I have $100 and you say I have $100, those are exactly the same. They mean the same thing, right? So fungible mean that it's perfectly exchangeable. It's perfectly the same, one versus the other. So is Bitcoin fungible? Not really, right? There is a history of transactions that is attached to each Bitcoin. And if one Bitcoin is just mined versus one Bitcoin is having some history of dark market transactions, then this is not the same as this one, right? In value terms, they are the same, but in fungibility, they're not really the same. In terms of privacy and in terms of history, they're not exactly the same. How about Ether? Those of you, do you know Ethereum? So we will discuss it a little bit later. Okay, so store of value, reliable store of value, retrieval and reuse. Value should remain stable over time. So with normal fiat currencies, with the currencies which the governments issue, do we have them stable over time?
Not going all over the place like
So that's the exchange rate between Polish currency and non-Norwegian currency. And then when I came here in 2013, it was, here, and now it's, here. So it's like 25% difference, right? Which is huge. So if you have any savings, you really feel the, the pain of the currency change, right? So they are stable, relatively stable, but they are not really fixed. They are fluctuations, right? And then if we, see this, so we have up here and down here, right? You see the fluctuations are much more wild, right? It's not 20%, it can be 100%, right? It can go half price quite quickly, right? So here we go, we're hitting almost 20,000 and now we're down to, it's more than 50%, right? So there are kind of a wide fluctuations up and down happening in cryptocurrencies. So the requirements for kind of a should remain stable over time, it's really hard actually, right? We don't know how we can do that. And not typically financial institutions do it by diversification. So if you have some sort of portfolio and you want to store a value for a while, you will sort of split it into chunks and invest some into gold, some into property, some into companies, and so on and so forth, in the hope that if one of the segment of the economy goes down, the other doesn't, is not affected that much. And if one goes really up, the other is not affected. So you're kind of trying to stabilize your portfolio over a number of kind of risk factors. Okay, so we do use electronic currencies, digital currencies, much more than the cryptocurrencies. We did have cashless payment systems for years. We've been using kind of Visa cards or electronic payment systems for a number of use cases. So we have the kind of a banking sector using the digital tokens as currency. For a while, we had virtual currencies like game coins in games. We had an equivalent of a digital gold. So gold is often used as a currency, but it's actually quite cumbersome to carry gold around. So if I buy 1 kg of gold and I want to store it, I don't want to store it at home. I will store it with some provider. So the provider will kind of have it in the safe for me, and I will just get a piece of receipt that says, okay, you have 1 kg of gold stored with us, right? And then if I want to sell you 100 grams of it, I just give you part of that paper, and then you own part of it, right? And you have kind of a digital coin which represents gold. So we did use it for a number of use cases before. As in particular, there was this digital gold currency, which was similar to the US gold certificate model. It was representative of the real money. It was kind of global, and you can technically exchange it for gold on demand. It was only exchanged electronically. It never had physical representation, and the transactions were non-reversible. So if I issue a transaction by giving someone 100 grams of my gold, I couldn't revert it, right? Do you know of financial systems which are reversible? So do you know of any system that allows you to revert the payment? Yep, with some of the credit cards, you can say, well, that transaction, I haven't initiated it. It's some sort of a scam or some sort of a glitch or something happened that I was not an author of that transaction. And if you do it quick enough, or if you prove that you didn't initiated it, some of those transactions can be reversed, right? So the bank may say, actually, the funds will never get to the recipient address. So if you block your card, the ongoing transactions will be sort of reverted back. So if you lose your card, you can do that, and then whatever someone was trying to use your card for is likely not to go through, right? This one was non-reversible. So what are the advantages of reversibility or non-reversibility? Yep. Why this digital gold currency don't have reversible transactions?
I don't know about that, but reversibility is good if in case you haven't used it, then it can be reversed and you won't take the impact.
Yeah. So it's harder to implement because you have to have some concept of the atomicity, and you have to take into account this buffer of things that are kind of not confirmed yet, right? So having non-reversible transactions is easier to implement because the moment somebody issues or signs something, that's it. There is no reversibility. So the system in itself is simpler, right? Okay, so we sort of distinguish between soft and hard electronic currencies. So soft, you have a reversible payments. The clearing time is usually, 72 or more hours. So they take time to actually clear. So if someone sends you funds by one of the soft electronic currencies, you have to wait for the money to show up on your account. It doesn't happen instantaneously, right? They need to handle disputes. Right? So I say, no, I didn't send it. Yes, you did. Reversibility has its consequences. And, credit cards and PayPal are the examples of soft electronic currencies. Hard electronic currencies, you have non-reversible transactions. So once the transaction is signed or initiated, that's it. There is no going back. You have instant clearing, right? So the moment you give me the funds, I have them. I don't have to wait for the clearing like here. They are simpler, no dispute handling. So some of the banking currencies and some of the digital gold currencies. So with my bank account, if I send the money to the same bank, it's instantaneous and it's done. If you do cross-bank, sometimes you have to wait because the banks will use some sort of a clearinghouse as a safety measure, right? So between banks, usually it's 24 hours or 12 hours. Within the same bank or the same bank group, usually it's instantaneous. So all of the banking ones rely on computer network. They rely on some sort of cryptography system. They are linked to some sort of commodity. And they use a form of private public key cryptography for signatures, right? So what is a blind signature? I have a slide for that. So the normal signature is that if Alice wants to sign something for Bob, right? So Alice prepares a message and signs it with her private key. Then Bob can use Alice's public key to verify that the signature matches, right? So blind signature is basically the same concept. It's just that Alice doesn't need to know what's inside them. So I can have Charlie preparing a message, and Alice can sign it. So Alice, like Charlie, puts it into an envelope in such a way that she cannot read what M is, but she can still sign the message, right? So then Bob can verify that, yes, the message was signed, even though Alice doesn't know what's inside, right? So blind signature allows me to sign somebody else's message without them being able to manipulate or change it later, without me learning what it is and then proving to somebody that, yes, I verified that the message is what it's supposed to be. Okay. So we can use it for voting system. We use it for verifying things that you don't want to link to the original author, right? We want to maintain privacy without revealing of who was the original author, or without revealing the content for the signer. So the signer can doesn't learn what the content of the message is. Okay, so centralized versus decentralized. So all modern currency systems are centralized. They have some sort of authority which manages the system. Gift economy, barter, commodity economy, all those previously discussed economies, they didn't have a central authority. Even the Kai stones, there was no authority, just people agreed. There was a concept of kind of consensus of what those huge round stones mean, right? So decentralized systems are kind of fit in here. And with the modern technologies, this, like, you know, we started with this. We as humanity, we were using things like this. Then we moved towards centralized systems where governments or kings were issuing, you know, coins and so on, right? And now with modern technology, we kind of re-evaluating and exploring some of the decentralized models for a number of reasons. So one is the kind of being in control of the financial system. So who has the oversight, who has the ownership of that, who can manipulate it. The other one is a lot of systems allow you to sort of exchange cross-border without the need for very complicated trust authorities. You can do certain things without the kind of a trusted third party. And we don't know all the implications of that yet. It's like the space is very quickly moving and kind of, innovative. So one of the first examples of the electronic cryptocurrencies is Bitcoin. So it has been described or released as a white paper in October 2008. And then actually the chain was launched in January 2009. It is a decentralized currency, fits into the kind of a barter economy model. It is representative, so it's not linked to any physical goods, right? It only has kind of a representative value. So people who are using it, they have to agree what that value is. No central authority gives it a value. So it's exclusively driven by perception and by people agreeing of the value. If all the people agree that Bitcoin is worthless, the price will be zero, right? So it is very interesting from technology, finance, and social aspects, mechanics, right? So it has interesting incentive model, and it's sort of a self-regulating and peer-to-peer. There is no central authority. There is no one actually deciding on things. It's by nodes adapting a particular patch or adapting particular software that things get changed in Bitcoin. So it is a form of electronic currency, a software system distributed database. It is decentralized, no central authority, no clearing houses, peer-to-peer payments, but they have to go through the chain. It's not reversible, so once you make a payment, it cannot be reverted. And all transactions are recorded in the ledger, right? So it has some of the properties which we discussed, and it kind of belongs to the hard digital currency model. So a total number of coins ever generated will be 21 million. That's the kind of a hard-coded limit of how the money supply will work. The smallest unit is 1 Satoshi, and then 1 Bitcoin is 100 billion Satoshis. A block is a store of unit for the transaction bookkeeping. A single block consists of a number of transactions, and then the first transaction in a block is special. So for example, you can use some block explorers to see different blocks and their content. So we can go to block info and check this transaction. So we currently at the transaction or at the block 508,000, and we're going back in time to this block. So let's check this block. We see it only has one transaction, right? It's a one transaction, and the total output is 12.5. So the initial reward was 50 Bitcoin for mining a block. Then it gets halved roughly every 4 years. And at that point in time, which was it was actually the lecture last year we had. So that block was the up-to-date block that we had last year for the lecture. And it says, okay, there is one transaction only. It has 12.5 Bitcoin going to this address, right? So there is no input because the reward is a special transaction which kind of generates money out of thin air. There is nothing really attached to it, and it gets to this input, and then you can check, if any, how this has been spent, right? So you see that this transaction belonged to the F2 pool, which is a mining pool, and it has been spent so we would need to check what was the address. So that's the block. Yeah, so that's the generated one, which transfers the funds to the yeah, so the address is a very fat address which is used for a number of transactions coming in. So we have 45,000 transactions going out, through that particular address. So this address is kind of heavily reused by the mining pool. So it's kind of really tricky to be able to track where exactly the 12 coins go, because you have, a huge number of transactions, kind of, 45,000 happening on that single address. All right, so we have the concept of mining, which means the block. So we have the genesis block. So that's the block number 0. And then every subsequent block has to be kind of discovered. And the process goes that this block discovery takes about 10 minutes, given a kind of a hash power of the network. So they have to kind of solve a hashing function, and the mining difficulty sets the task such that the entire network takes roughly 10 minutes to do that, right? It's completely random. You have to use a kind of a brute force search to find out what the puzzle solution is. And the puzzle is set up in a very simple way. So I will just go, so the block contains of the version of the protocol, the previous block hash, so the hash of the previous block. So, you sort of root it at the previous block, a Merkle root for all your transactions, so the hash of all the transactions that are in the block, the timestamp, so timestamp, current difficulty, transaction count, and transaction data, so all of this, and the nonce. And the nonce is the thing you can manipulate, right? So you can check different nonces to hash all the data structure that you have to hash. So this is the only one that you can manipulate to hash and get the hash for the block. And the difficulty is that you would like to have a hash with, the hash is kind of a string of some random characters, and you would like to have the hash with the prefix of a certain number of zeros, right? So the hash space is totally random. Every time you're changing the nonce, you have the avalanche effect, so it's completely, you can't really predict how many zeros you will have up front. Sometimes you have none, sometimes you have one. But if the difficulty says you should have such and such number of zeros up front, the harder it gets. The longer the zero count is, the harder it gets to find one by random chance, right? So the difficulty controls how many zeros are at the beginning of the hash, which hashes the block. And the first miner who discovers that hash with a particular nonce announces it to a network and says, okay, I have the new block, right? Which is kind of attached to the previous block, which hashes the transactions and has a particular properties. As we've seen with this block, this block doesn't contain any transactions, right? Why it is useful? Why would you do that? Well, normally you shouldn't, right? So normally if you're a miner, it takes you roughly the same amount of time to find a hash for something with transactions and something empty. But the protocol doesn't prevent a particular mining pool to mine empty blocks with no transactions, right? What's the benefit of the miner including the transactions? The benefit is, so let's check the latest one. Blockchain info. So that's the one which was generated 7 minutes ago. So on average, it should be 10 minutes, but you see between these two, it's 7 minutes. Between these two is 6 minutes. Here, 2 minutes. So it feels like the difficulty is too easy, right? But the network will adjust. So if there is more blocks being generated, on average less than 10 minutes, the difficulty will get cramped up. So it kind of doesn't follow every block. It happens up to, we have it. So here, roughly 2 weeks. It takes about 2 weeks for the difficulty to adjust, right? So the more miners come into a network and the more mining power there is, every 2 weeks the difficulty gets adjusted. So now, yeah, possibly it's getting a little bit easy, so there will be an adjustment. So if we check this one, we see that we have we have a number of transactions which are included in the block, and the first no input one is 12.621. Why it's not 12.5? So the miner who discovered the output, the hash, has been given a reward plus some extra. Where is the extra coming from? So it's 1.20, yeah? Transaction fees, exactly. So every transaction which is in the network, it has to have a little bit of the fee that is attached to the transaction, which gets summed up into the total reward that the miner gets. So it's in the miner's benefit to include transactions, especially the ones with largish fees, in such a way that it gets more reward, right? So every 2 weeks the difficulty gets adjusted, and then every about 4 years the reward gets halved. So it used to be 50. Yeah, so when I started mining Bitcoin, it was already too hard to get 50. So I had to be part of the mining pool, because waiting for your miner to be able to find out the full block was too long. I don't remember, maybe like 2-3 months. And therefore you don't know, it's kind of a random process. You're waiting for 3 months, kind of doing all those calculations, and nothing happens. With the mining pool, even if your miner doesn't find anything, you still get shares from the mining pool, right? So I never experienced the full award from the network, but then it got halved to 25, and now it's 12.5, and then it will get, it changed, in 2016. So roughly speaking, 2019, 2020, we will have the next halving. Okay, so we have the concept of forks. So the chain is composed of the genesis block back in the past, and then each block is attached to the previous block, right? So now let's say this is the latest block. That's the block number 508. That's the block, okay? So with the ending 966. Okay, and there are different mining pools mining, okay? And let's say one discovers a block, which is 967, and says, look, guys, there is the 967 block, and it broadcasts it into a network. And it takes a while for all the nodes to hear the broadcast, right? Because the information has to spread through the peer-to-peer network. And while it is happening, another mining pool discovers also the hash with different nouns, which hashes to the same difficulty, which says, oh yeah, no, we found 967, right? So you have a peer-to-peer network, and part of the network sees the announcement from A, and part of the network sees the announcement from B. And the announcements kind of collide, so this node hears the announcement from both places, maybe from A first, right? So once a node hears an announcement from a particular place, what the node will do? By default, it accepts the one which it got first, right? So if the node got announcement from A, it will sort of get to A. But there is kind of communication happening between the nodes. So the announcement happens, and at the end of the announcement, all the nodes will be either A or B, right? So the network gets partitioned, right? So part of the network believes A win, part of the network believes B wins, okay? They don't change their mind, okay? And now, if there is, obviously, this miner, because it discovered the block, it hopes it will be the one which wins. It starts mining immediately, again, using that block as the next block, right? So it tries to mine next one. Same happens here. This one tries to mine another block, right? So what will happen now is one of them will get first, okay? Or you may have, so you have mining pool A, B, and C. C lost the battle for 967, but as soon as 967 was announced, let's say C got the version of B, right? So C mined somewhere here, and it got the announcement from one of the B nodes. So C also mines. And now C discovered the next block, and it announces 968. It says, look, I have 968, right? So now C makes a broadcast which says, look, I have a 968. So some of the nodes now kind of hear the announcement, and then they become sort of they become attached to the C version of the top of the chain. And then the announcement kind of spreads, and then the previously A nodes will learn there is a new node, which is 967. So they are still thinking there is a 967, which is version A, right? And then now they hear, so there is, okay, let's see this. So if I'm a node, and I believe A967 is the top of the chain, and I hear an announcement that there is a C968, which is the top of the chain, and the the previous from C is B967, which is in conflict with which I knew from previous announcement, right? So then a node will check, okay, which one is longer? Is this one longer than this one? It is, because I'm one block after this one, right? Which means this one is one block after this one. I will drop my belief and I will switch to the longest one, right? So now the nodes which hear the announcement from C will say, okay, because C announcement forms a longest chain, I will prefer that, okay? So they will switch to C. Okay, so the network will kind of start believing C is the winning now. Okay, and what may happen is A generates 968 and 969 in quick progression, and announces that. It announces, look, I have 969, right? So there is an announcement says A969 now, and again all the nodes will check. Okay, is it the longest one? Yes, this one is the longest one. Okay, so now you will have the history kind of like this, and you will have a kind of a orphaned fork, which happened up to 968, which goes through the B discovered node and then from C discovered block. But then it's sort of the network now is all here, and if the next one is also based on this one, then that's it. That's the end of the game. There is no more hope for any of those miners to be wasting time mining from this block, because it's much more profitable to mine here because you are more likely to be accepted than from here, right? Questions? Yes?
What's the longest parallel running chains?
Yeah, that's a good question. So I don't know the answer. But it's a good question. Bitcoin longest forked. Oh. The orphan blocked view shows a recent fork of the blockchain starting that went 4 blocks. Okay, so the longest one seems to be there was a bug. So yeah, I do remember the bug. There was a bug in the wallet software, and they released the software, and then after a while they said, oh shit, there is a bug, right? So the bug allowed some misuse of the funds. So while some people were downloading the new wallet and using it, the most of the community said, okay, you know, you should not do that, right? So the people who are using the buggy software, they did some transactions, and then majority of the network didn't update it to the buggy one, they updated to the fixed one. And then there was like a fork which went for 53 blocks sideways, and then the most of the community were using the proper wallet, and they slowly took over that one because no one wanted to mine on the, you know, broken fork, right? So even though that one was way longer, the updated wallet software was not using the blocks from the fork. They were using the blocks from the where it happened, when the bug happened. And then they kind of overtook the fork because by consensus no one was mining the, you know, the problematic fork. But that's very unusual. So the normally you can assume it's not more than 4, right? So why is this question very important? Yeah?
Because it depends if you get the money for the block.
Exactly, because if it happens that you got a transfer in one of the orphaned forks, you can check the blockchain and says, yes, I got the money, and then few blocks later it turns out you are inside the orphaned fork, then you doomed, right? You don't have the money, because this is the real history which everybody agrees on, not something in this block. So if your transaction, if the money coming in are here, and you gave your laptop or your car to someone, right? And then later on you discover, actually, I don't have the money, right? And they didn't spend the money. They still have the money. Even though they did spend it inside here, you know, it doesn't actually belong to the history. So that question is very important. So, you know, 4 blocks, roughly 10 minutes, roughly an hour, right? So that's the common rule of the thumb in Bitcoin, that if you want to confirm, you have to wait for, say, 6 confirmations, which is about an hour. Waiting for 3 or 1, not enough. Any other questions? Yeah.
So these A, B, and C, they all were part of the same mining group?
No, they can be of different mining groups,
Okay.
right? So I was kind of having A as one mining pool and B as another and C as another, right? Usually when something is discovered in a single mining pool, they immediately start mining from that block and announce it, because they want to have a little bit of an advantage of like early start. And that usually happens. Like you can see the mining pool that discovered the block is usually statistically at a little bit of an advantage situation compared to everybody else, right? So once something is discovered in one mining pool, they start mining for the next block. But there is also kind of an interesting dilemma, okay? So let's say you mining, we mining 6.7, okay? 6.6 is stable, and everybody is mining 6.7. And you're mining 6.7, and then there is an announcement that 6.7 has been found. Should you immediately drop mining 6.7, or should you go for a little bit longer, and then if you find it, re-announce? I don't know. So I don't know what's the strategy miners use. Usually they drop, right? Usually you want to be mining from the one which was announced to have a kind of a fast investment. Because at the end of the day, if your block is in the orphaned chain, you're not gonna get your reward. You're only gonna get the reward for the ones which are the longest. And you have to wait a little bit, I don't remember how many blocks, but to actually cash the reward, you have to wait 10 blocks or something, yeah, or more. We can check that. Yeah, I don't know. I don't remember. Yeah, there is a question of why Bitcoin miners dedicate time to mining empty blocks. That's kind of, again, a philosophical dilemma. You should, like the mining pools which mine empty blocks are considered harmful because they don't bring any value to the network. They just get the reward, but they don't actually provide any service to the network because they don't include any transactions. Sometimes, as you've seen here, the reward is quite small. So the reward here was like 0.12 Bitcoin, right? And you do waste a little bit of time because you have to transfer all the transaction, all the data to all the miners to mine that transaction, right? So if the block is smaller, you have less data to transfer, it will reach your mining pool faster, and you will get a little bit of an advantage, right? So statistically, it's a little bit in your favor to mine empty blocks, but it's frowned upon and it's actually punishable by, by the network stakeholders that you're not supposed to be doing that, right? It may naturally occur if you have no transaction pool in the pool at the moment, right? So let's say 969 has been just discovered, and I want to immediately start mining new blocks, and I check what's the ongoing transaction. And recently, that's not likely to happen because there is a lot of transactions. But in the, back in the day, it was possible that there was no transactions, right? In the last 10 minutes, nobody was sending Bitcoin to anybody. And therefore, you just mine an empty block. These days, that's, statistically impossible. Okay, any other questions about the structure of the header and the mechanics of mining and the mechanics of choosing the longest chain? We have a question, what is a Merkle tree? So I was saying that there is a Merkle tree hash which needs to be included into the hashing of the block data. What's Merkle tree? Anyone? It's a very simple concept. So all my transactions, so I have a transaction, and the transactions have hashes. So a particular transaction that happened is sort of validated by the hash it has, right? And then I can organize the transactions into a tree. So I can have transaction as leaf nodes, and then I can group them. Okay, let's skip those, and then have a hash, which is a hash of those hashes of A, B, and C, and A is the hash of A1 and A2 and B of B1 and B2, right? So this is a hash also of these two, and these ones are hashes of the transactions. So if I quickly calculate the three hashes, then to validate all those transactions, I only need to validate the root hash. If the root hash matches, that means all my transactions in the data structure are correct, right? So Merkle tree is basically a tree of hashes where each junction is a hash of the children, and the leaf nodes are hashes themselves. Okay, right. So now comes the hard bit. The hard bit is that we need to track who sends money to whom by following the transactions, okay? So the transaction sort of looks like this. I have the in address, I have the out address, and I have the amount. And if I have an address, I have a particular amount inside this address. So let's say I have 1 coin, right? So now if I want to spend this, I have to spend the whole thing. I cannot spend part of the amount that the address has, right? So normally if I want to pay someone, I will pick one of the addresses that I control. I kind of provide a proof that I own it by the private key, and then I have to spend it. So I will have kind of outgoing transactions, and I will have one, which let's say this is A, and this is address owned by B. So B just generated a completely fresh address, key value pair, I mean public-private key pair, and it's B owns the private key to this public address. It sent the public address to A, so now A made the transfer, right? So it sent, let's say, 05 to this address, right? So 05 will now be owned by this address, and it will be kind of unspent output. It will be called unspent output because the output of this address has not been spent yet, right? Whereas this guy will have two outputs, one which goes here, and then one I have to do something with the 05 coins, right? So I can generate for myself, A can generate another address that puts the 05. In fact, it will be a little bit less because I have to include a fee, right? Let's say we pay 01 fee. So I will have 04. So now kind of the spent is 09 and unspent is 01. And this one goes to a minor, right? Because this address is kind of gets 0. It has to get 0 at the end, right? Okay, so this is one case. And that's what Bitcoin original white paper was suggesting, that every time you're spending some money, you generate a new address and kind of have the change going to that new address, right? In fact, it was suggesting that you should generate two addresses and then make the final payment from the intermediary address as well, right? So if this one has now 0, this one has 0, this one has half, this one has 4, and the unspent one went to as a first transaction in the mining block. Some wallets don't do that. Some wallets would say, okay, instead of generating the new address, let's send it back to the same address, right? So instead of generating new address, I will end up having 04 sent back to this one, right? If you see something like this, you know there is a change coming back to the owner and the payment is between somebody going here, right? If you see the original one, you don't know because you have to kind of track the tree. You don't know whether this is a change or whether this is a change or whether it's just a payment split, right? I'm actually not transferring anything. Everything still belongs to A, right? So there is this concept of kind of clustering, right? So we want to cluster all the addresses which are being generated and used in transactions to sort of roughly estimate what's the probability that the cluster belongs to A, right? Or particular entity, right? What's the probability that this belongs to A? Almost 100%, right? What's the probability that this one, that this address and this address belong to A? Well, you don't know. I mean, you can have some heuristics and you can have some estimation based on what happens later with the funds, right? If nothing happens to this node, and you knew this belonged to A, and something happens to these funds, usually you can assume, okay, probably that was the payment, and the payment has been used for something, and this one isn't. And also it depends what, because if you have the, if you imagine all this, yeah, now the question is, what is DAG? What is DAG? Do you know? Yeah? Directed acyclic graph, right? So it's a directed graph with no cycles, right? So what does it mean? It means that typically when you, because we want the, yeah, let me see. No, that's just a discussion. Yeah, let's see here. Yeah, so some addresses are marked spent, and some addresses are marked unspent, right? So, you know, initially everything starts with Satoshi. Satoshi had the initial 50 coins of the block award, and you know, he kind of, or she, or the group spent it. Right now, the miners kind of mine the award. They have the award in a particular address, and then they spend it. So they send the money. Let's say I got 12.5, and I spent, you know, I spent the money half to someone. Okay, so now someone is rooted here because you know the miners. You know the miners because they are the first transaction in the blocks, and then someone will get the money, and then you have the cloud of how the payments kind of look like, right? So even though I can loop back, I can say, okay, I'm spending some money here and some change comes back. I can convert it to a DAG because I know I have a certain amount of funds which are still unspent here, right? So instead of saying I have a cycle, I say there is no cycle. There is 03 or 04 in our case, and let's say there was one coin 04 and 05, right? I'm really only interested in tracking all the unspent leaves or unspent leaves of the tree, right? So I want to have a directed graph of all the funds which are kind of ending up in the leaf nodes which have no spent coins yet, right? All the parents will have at least one transaction going out, so part of the funds are spent, right? These guys can have 0, or they can have they can have more, but these guys always are non-zero, right? Non-zero, the leaves, because they have kind of unknown spent transactions. So I can generate this, and then I can try to cluster, right? I can kind of try, okay, I think those belong to one entity, and those belong to one entity, and so on. With the leaves, it's really hard to tell, because the leaves have not been spent yet, right? So usually you kind of group the leaves to the cluster that they are kind of coming from, right? But you don't know, like, you know, if you have an entity, let's say, you know, you have some transactions and you identify this is a mining pool, and the mining pool, an exchange, and the exchange transferred some money to this guy, and this guy never spent them. You don't know if it still belongs to the exchange or it's a new owner, because if it's a new owner, you will see some characteristics once the money are being spent. If the money are just sitting there, you have no knowledge. You have no idea whether the money belong to a third party or whether they belong to the cluster that you already have, right? So For those leaf nodes, it's very hard to tell. For the nodes which are inside the network, already in the DAG, you have more and more knowledge how to classify them, right? Okay, we went a little bit over time, so let's have 5 minutes break. Okay, 5 minutes break. I will change. let us continue. So we talked a little bit about the DAG and a little bit about the tracking transactions. So let's have a check how it actually looks in practice. There are forensic tools that are quite expensive, and even for the law enforcement, they're quite expensive. So I don't have access to the to the proper tools, but they kind of look similar way to the blockchain info. So if we go here and we check, I will close some of the tabs. Rice stones. Okay, so here we have a particular transaction, right? So we see that there was money coming out, 433 in total, going into those two addresses, which were both spent. And we see that the total input was 43339. Again, that's a little bit of a heuristic, right? If you see values which go 8 decimal places on Satoshi, then you know, well, it's probably not human entering that, right? You know, most of the time, if you go 3 or 4 or 5 decimal places, that's kind of a human. But if it's more, that's usually either a change, some sort of leftover, or because, you know, you don't specify prices for things in 8 decimal places up to, you know, sub-cent values, right? So you can use a bit of a heuristic of judging which one goes where, right? So here we have the 0.08 fee being left over, and the total output is 4359, and then we have this 3.33 and this, which is 99.59, right? Which one looks more likely as a payment and which one looks more likely like a fee, not fee, like a change? Well, it's kind of hard to say. Usually the smaller one is the payment. Here the smaller one is actually quite nice number. It's 333. So it's kind of hard to say which one is the payment, which one is the fee, but likely this is the change and likely this is the payment, but you know, you don't know. So you can sort of go here and you can visualize the transactions kind of visually, and then you see the original transaction with the unspent output and then how the output was spent, right? So you can see it went to this and this, and you can kind of unfold and you can see, okay, this was spent subsequently here, and you can see the IP address of the original transaction and that one, which indicates, okay, possibly a change, right? This one has a different IP address, right? So someone most likely transfer money from here to here, and then that was the change. So if you were doing some clustering, you would probably say, okay, the origin and this kind of belong to the same cluster, right? And you can do some clustering here by IP addresses, and then you will see that it kind of it kind of looks the same with the same coloring. So then you can kind of unfold and you see, okay, the funds from this went here into a huge kind of pocket, right? There is some sort of a big address which stores quite a large number of coins, right? So, you know, it's very easy to see, okay, that 209 coins belong to one person because it's in the same address. You have to have one private key, right? You know, usually it's just one person controlling that. And then you see some sort of location of where the transaction kind of was happening from and to, and you can kind of browse again a local host, and you see from this 209 it splits into two small payments, and the bulk kind of gets transferred somewhere, right? So you see, okay, this and this almost certainly belongs to the same person, and this, right? So this, and this very likely belongs to the same, and then you can kind of carry on, and here we get to something interesting, right? So from this account, which had 171 coins, you see something interesting. Okay, a massive number of transactions splitting up, some very small and some getting kind of bigger. So, doing it visually, it's a little bit tedious, right? But if you have some clusters and those kind of link you back to the same clusters, you can kind of collapse them, right? So okay, those funds are controlled by some sort of unit that you have. Another thing like this will happen when the mining pool distributes the funds to the miners, right? So it's very likely that this is a payment for the mining pool once a month or once in a while, saying, okay, that's your share, and off you go. And some small miners will get some small, awards that they accumulated, and some bigger ones will get bigger ones, right? So it might be the case that that's sort of a mining pool paying out the miners. So then you can tag, okay, this is very likely to be a mining pool, right? Or something. So there is a number of heuristics people use, and there is a big value in collecting data of known addresses belonging to mining pools or the anonymization services. So we kind of discussed this, and it is clear to you that it's kind of really easy to track the transactions in the Bitcoin blockchain. They are not in the plain, they're not linked to identities, but they do allow you to do analysis and track. So there is, we a little bit running out of time, but there are two important concepts here. So one is that some transactions, like if you have some coins, you want to make it harder for the tracking to kind of track your transactions, right? So if I have an address and I have some coins here, so I have this address and I have some coins, and it kind of is linked to me somehow. I bought the coins via an exchange or whatever, right? And now I would like to have this amount, let's say 1 coin, in an address which is completely not linked to me, right? I would like to use some sort of a service which allows me to anonymize the coins I own. So we would use some sort of a mixing service, right? A mixing service works like this. So there is a mixer. People submit some coins into the mixer. The mixer generates completely fresh addresses. And then, I mean, you basically have to have a private key to that address. So you submit somehow the address, the public part of the address, to the mixer. So the mixer will say, okay, there is the money coming in and money coming out. And money coming out are going to these public addresses, which I know because you have to submit it, right? And now they kind of make a link. They kind of shoot you the money to here, but they do it in this type of payment, which happens kind of across the board, right? So you have some money coming in, and then the mixer has a pool of coins, and from the pool of coins in the same wallet, they kind of disperse the money into the output addresses, right? So then if someone spends this money somewhere, let's say to buy drugs, the law enforcement can track it back to here, and then it's really hard to link this back to here, right? again, there are some heuristics. If the mixer allows different type of incoming values, right? You can have a value. So if I have a value of 1, roughly 1 on both ends, and here I have, 10, I don't know, 131, whatever that is, right? If the values are widely different, I can kind of correlate. It's very likely that the money coming in to a mixer is this one. I need to know the cluster for the mixer. Knowing the cluster for the mixer can be already challenging. And some mixers don't allow values more than like particular value, so then this correlation by value is hard as well. The correlation by time coming in and coming out is also hard because some mixers take up to 7 days, right? So they can store transactions for a number of time, and then if you're doing the tracking based on timestamps, you can't correlate those events neither. So there are some challenges kind of deciphering how the mixer actually anonymizes the coins. What you can do is you can ask the mixer operator, okay, can you tell me who got money, who transferred money in for this address, right? The mixer operators, if they are running in the dark web, they usually delete those records. They don't have those records. But you may have some which keep the records, right? In which case you will have the link between the public space and the sort of anonymized space. So again, there is different heuristics and different things to watch out for. So that's one thing. The second thing is not all. So we discussed the kind of a very simple transaction, which was sort of let's say pay to address, which is actually pay to public key, right? So we were paying to a public key which someone with the private key could claim. There is, yeah, let's see this transaction again. So if I go back and I have this original transaction spending the funds, I can go here and I see that I'm basically spending money to a public key, right? I have the public key encoded here and here, which are equivalent of those two outputs, and I'm basically spending money to a public key. What I can do here, there is a transaction type which is called pay to hash, script hash. So this one is quite inflexible because it kind of only makes the transfer to a single public key, right? What if I want to pay, like what I want to lock a money and kind of make more complicated payment somewhere to two people, right? Or for a person and the change. I can have a script which allows me to manipulate the transaction in such a way that it's more complicated than just the single instruction that we've seen here. So here it's kind of just right there, and the hash of the public key is right there. But with pay to script hash, I can have a hash of a script, and then when I am locking the funds, I have to submit the script, which needs to hash to the same value, and then it will be executed as part of the spending of the transaction, right? So then there will be a signature operand, which is the public key, and then there is a checking for the validity of the provided data. And for this to work, I have to have some sort of a virtual machine or some sort of a language which allows me to do those things. So Bitcoin is one of the simpler ones, which uses kind of a Forth-like programming language, which is stack-based. Do you know Forth? It's a kind of an old programming language where you can, it's a little bit awkward because you're using a reverse Polish notation. So you're kind of specifying the operands first and then the operation that will happen on the operands. So for example, to add two numbers, you would say 3, 5, add, right? And it means put 3 on the stack, put 5 on the stack, and now call add on those. So it will kind of result in 8 on the stack. So you kind of do the reverse Polish notation where you start with operands and then the operation kind of comes later. And you can write your programs, you know. So let's say if you want to multiply it by 2, right? If you want to multiply 8 by 2, you would say 2, 3, 5, add mul, right? So then I would have 2 on the stack, 3 on the stack, 5 on the stack, add these two, 8, and then multiply these. So I will end up with 16 on the stack, right? You can also write it like this. So do this with those two operands, put this on top of the stack. So then I would have this and the gap with 8, and then put 2 on top of the stack, and then do this, right? But if you change it to divide, the semantics would change completely, right? Because now I have the operands turned around, right? So if I want to divide 8 by 2, I would have to do this. So Bitcoin is using kind of 4-flag language where you have those operands and you see that here. So I'm saying, okay, duplicate what's currently on top of the stack, right? And then calculate a hash, the 160-bit hash on top of what the duplicate was, right? So I have a key, and then I'm duplicating the key, calculating the hash. Operations usually consume what they take, right? So like the add will eat those two, and so hash will eat whatever is on top of the stack. So if I have because the output script, I have to supply my public key to or some proof, which then gets duplicated and hashed. So then I can compare. Equal verify will verify what the output of the hashing was with what was supplied here. So this is basically the hash that you have to demonstrate that you have access to generate based on the transaction that you're spending. And you can only do that with private key. So then this comparison happens by equal verify, and then the checking of the signatures happens at the end. So it's composed of opcodes. It's Turing incomplete. What Turing completeness means, that I can write arbitrary logic, right? If I have a Turing complete system, I can write loops and I can write complicated procedures which will take as much computational resources as given, right? This language doesn't have that. It only has very primitive operations for hashing, checking signatures, encrypting, duplicating, and so on. But you can express quite a lot of logic with it, right? So what is the fundamental data structure in Forth? Stack. It's kind of a stack-based language. So everything you do is with the stack, basically. Okay, a bonus question. What are the necessary instructions to enable Turing complete computing? So if you were to design a virtual machine which would have the minimum amount of instructions but be able to express any computing program, what that would be? What do you think? So what are the necessary instructions to enable Turing complete computing?
In terms of virtual machines.
So what instruction set would you need to have So then you can, like, if I have any program, okay, let's say you have okay, I have Java. Any program written in Java, can I write a C++ program that will be the same? So any program I write in Java, can I write in C++? Yes, I can, right? And this gets compiled to, you know, machine code for, let's say, ARM CPU, right? Okay, so now I'm asking, and Java is quite complicated. It has a lot of instructions. C++ also is quite complicated. Forth, can I write any program in Forth that is expressible in C++ and then compile to ARM? I can, right? So Forth is simpler. It's a simpler language than those two. I'm asking, okay, what's the simplest language that I can express anything and then execute on ARM CPU? What instructions do I need to have here? Yeah, but give me examples of instructions. So addition, do we need addition?
Mathematical computation.
Yeah, so mathematical. So mathematical, math, addition. Do we need multiplication? No, I don't need multiplication. I can always convert multiplication to addition, right? Okay. Do I need subtraction? Can you substitute subtraction with addition? So if I say 2 minus 3 is the same as 2 plus minus 3, right? I can substitute. I don't need subtraction. Okay. So multiplication, I don't need. Subtraction, I don't need. Okay, addition will do fine. Okay, I need logical operations, right? So what sort of logical operation do you need? Or and? Okay. Okay, actually, I don't need addition if I have and not, because I can simulate addition with and not. In fact, I can simulate everything with and not because I have a gate called NAND, which is pretty much the only gate which ARM CPU has, right? So if I have NAND, I can do that. But with NAND, I'm still missing one thing. I'm still missing control structure. I'm still missing if statement and split. So if this, do this or do that, right? Okay, so if you think about it, then the smallest programming language that you need on the virtual machine. So if you were to design a virtual machine that you can program anything, it only really need one instruction. And that instruction is, if a particular memory location is bigger than 0, add 1 to that memory location, else jump to a different part of your program, right? If you have instruction that can do addition, comparison, and jump, then you're sweet. You can program anything Java can do. It will be really difficult to program, useful things with that language, but you can convert C++ or Java program into that, right? Okay. So, yeah, there are some details about the language. I will not go over all the details. You can check it out. And then there is a kind of, so the guy says, thus for any non-deterministic Turing machine M that runs in some polynomial time P of n, we can devise an algorithm that takes an input of length n and produces EMW. The running time is on a multiple deterministic Turing machine. Well, I just wanted to program video games. I don't need to know all the theory about Turing completeness and all that stuff, right? but it kind of gives you some insights into the actual workings of the Bitcoin script and also of other cryptocurrency scripts. So there is quite a lot you can do programming the Bitcoin chain. You can inject some of the operations and some of the logic into the chain itself. The limiting factor is the language, but you know, with Ethereum, for example, you have a full instruction set. You have almost Java-like programming language, and you can program what happens to the funds under what circumstances, and you can program logic. So that's why Ethereum is sort of, or other modern blockchains are kind of gaining popularity because you can express much more over there. So there are three things that I want to finish with. So one is IPFS. How many of you know IPFS? Yeah. So what would you say it is? It's kind of a distributed cloud storage solution based on the mixture of Git and BitTorrent. Okay. So you have the idea of hashing content, and you have a content addressable storage. So if you want to search for something, you don't search it by address, you search it by the hash that it maps to. So it's kind of a content addressable space, search space, and then the content is distributed over a different number of peers, and they can kind of share it. So IPFS is very interesting because blockchains have difficulty storing stuff. Basically, what can you store inside a Bitcoin blockchain is a hash. And in IPFS, the hash is addressing the content, right? So it's a perfect match of combining some of the blockchain technology with storage, which IPFS offers. So that's one. The second one is Ethereum, which I already mentioned. So Ethereum offers a fully Turing complete instruction set and allows programmers and developers to develop kind of programs that are running on that blockchain. And you can have a kind of a complicated logic which is used for locking or releasing funds. Okay, and the final thing is Bitcoin is actually quite easy to work with in terms of tracking. There are other currencies and some other technologies which are, you know, different or harder. So one of those currencies is called CryptoNote. So if you check their websites, they kind of discuss how the payments are different to the payments in the Bitcoin network. So they have kind of a blockchain analysis resistance built in, and they're using kind of something which is called ring signatures. So in ring signatures, we still use public-private key cryptography, but we kind of hide who was the actual originator of the signature in a group, and it's provably impossible to de-anonymize the transaction that is sort of used this way, right? So you can check ring signatures, and like Monero is using ring signatures as well, and it's a technology which allows you to sort of improve the anonymity of the blockchain itself, of the data structures and the transactions which are happening. So have a read on the CryptoNote features, how they address double spending, how they address the verification and untraceability of the payments, and some other coins like Monero, for example, are using the same technology. There is a nice article. So Gwern, I don't know if you know. It's a British scientist who kind of writes essays, and he has a good collection of dark marketplaces data. So he has an article where I will put it onto the slides, which he kind of discusses the Bitcoin blockchain and the current blockchain revolution, because all the crypto that we're using for the technology is at least 10, 15, 20 years old. And he kind of calculated that if Bitcoin were to start, it could have started about 8 years earlier. It was not necessary to wait 8 years to build the Bitcoin blockchain, because all the building blocks, all the technology was known how to do it, like 8 or 10 years before that. So we are kind of rediscovering some of the ring signatures are not new neither. Same with zero knowledge proofs and some of the modern crypto primitives. We are kind of rediscovering ways of using it and ways of kind of utilizing the technology. So I kind of encourage you to check. I will put his essay onto the slides and check the crypto node and the ring signatures as an example. I'm not saying there is, they're not doing anything very special than other crypto, privacy preserving crypto, but it's a good write-up of how it is done. And there is a new emerging mechanism for doing Bitcoin transactions. So normally the Bitcoin transactions have to be logged into a blockchain, but we've observed that the Bitcoin blockchain got kind of saturated, and we don't really have proper peer-to-peer payments. So there is a concept of Lightning Network, which has been deployed recently into the main chain after a few months of being run in the testnet. And what it allows to set up a payment channel, sort of like a credit, between two nodes, and then make instantaneous transactions up to that credit limit between the peers. So I can establish a particular connection with any of you, and then up to my credit limit, we can exchange money back and forth millions of times per second as fast as we want without anything being locked in the blockchain. And that allows kind of a proper distributed and scalable solution for the payments. Those payments don't show up in the blockchain. The setup of the channels doesn't show up in the network neither, in the blockchain, but you can observe some of the closures of the channels. So we have a PhD student and a master student working at the moment on the project of trying to work out how can we observe the payment channels being kind of established based on the data which is visible in the blockchain, and what are the limitations of trying to do that. So that's one master project and one PhD project that we run. We have a PhD position for cryptocurrency tracking, which we're looking for candidates with the master's degree for. And we have two master projects currently being run in terms of anonymity and some of the cryptocurrencies which are used for banks and for government. So for example, Norwegian tax office is very interested in the technology for allowing people to calculate their taxes on their own, as long as they can verify that the calculations are not tampered with, because then they don't need to store all the data. They can kind of outsource some of the storage to personal accounts or to banks. So we're kind of investigating how private data can be used in such a way that public clouds can be used for storing it, or blockchains can be used for doing some calculations on it. So there is a number of master projects and research projects in the area. So yeah, so that's it. Any questions? It's a little bit hard to cover all the technical nitty-gritty of the tracking and the transaction mechanics, but I hope you get kind of an overview of the technology and of the different aspects of where to look for further information. We had one master project last year which was looking into security of Ethereum smart contracts, so how they can be attacked, what sort of attack vectors they have, how they can be made more secure. and what are the automated limitations of the existing security frameworks for the smart contracts. Yeah, all right. If you have no questions, that's it. Thank you very much.